Hey everyone. Today is going to be a quick review over the brain. It'll be a little bit longer than some of my other review videos just because there's so many different structures and so many different things to go over. But hopefully this is a nice kind of reminder of some of the different parts of the brain that we've discussed in class, some different ways to remember those parts of the brain. Know that on an FRQ, when I've seen parts of the brain show up in previous years, often what they like to do is they like to ask questions about what happens when these parts of the brain don't work anymore. And so it's important to know a lot about their function, and then also if there happens to be damage, for example, some consequences of that part of the brain not working well. So we'll start with the oldest part of the brain. And when I say the oldest part of the brain, I kind of mean this in two different ways. One, it's one of the oldest parts of your specific brain in the sense that it's one of the first parts of the brain to develop. But also, evolutionarily speaking, the hindbrain has the oldest structures, and they're the structures that are the most similar across all species. And so if you compare the hindbrain to a human, to a hindbrain of a chimpanzee or a house cat or a rat, they're all really similar. And I think that'll make sense when you think about the actual structures themselves. The medulla, for example, is the lifeline of our brain and of our body. The medulla helps regulate our heart rate and our breathing. And just like we need to have regulated heart rate and breathing as humans, so do house cats and rats and fish. And so we see medullas that are very similar in all these different species. Our pons help regulate sleep cycle, and they help us get tired in the evenings when it's time to lay down, and help make us more alert in the morning when it's time to wake up. And I always say, remember the pons they're at the top of the brainstem, and they're right here. They're kind of that bump part, and think it almost looks like a little pillow. And pons with a P, pillow with a P, think it helps regulate sleep. Your reticular formation is a band of nerve fibers that travel along the inside of the brainstem, and you can see them on this bottom structure here. And our reticular formation helps with alertness. So not so much the daily sleep cycle of the pons, but the alertness, such as if someone says your name, and your ears kind of perk up and say, "Oh, is someone talking to me?" And there's that kind of jolt of energy that we experience. That is your reticular formation. If you were to damage your reticular formation, you'd likely go into a coma. If someone was to stimulate your reticular formation, you would be completely alert. And even if you were in a resting state, you would all of a sudden be immediately awake and alert. And then in the back of your brain, what is sometimes referred to as a mini brain is your cerebellum. And your cerebellum helps with lots of things, but one of the big things that AP psychology hits home is your cerebellum's role in balance, and staying upright and having good posture, and walking around with balance. As we dive a little bit deeper into the brain, we have what are called subcortical structures, and sometimes you'll hear these referred to as the limbic system. And so whether it's subcortical structures or limbic system, just know that is a category of brain structures that includes all these structures I have listed on the left there. Your thalamus is like the control center. Your thalamus helps direct sensory information of where it should go in the body. And so as you see things coming off the screen, that information goes to your thalamus, which is then directed to your visual cortex in order to interpret what you see. When you hear my voice, that information goes to your thalamus, and then it's directed to your auditory cortex so that you can interpret what you hear. So thalamus is like Thalma, the receptionist in the office building that tells people, go down the hallway, go up the staircase. The thalamus is kind of the first place that this information goes, and it directs it to the different parts of the brain. Your hypothalamus, on the other hand, your hypothalamus helps us maintain homeostasis. Your hypothalamus is what drives you to eat when you're hungry, drives you to get something to drink when you're thirsty. We sometimes say the hypothalamus is like the bar in your brain. People go to the bar when they're hungry, when they're thirsty, when they're looking for sex. And so the hypothalamus helps with those internal drives that we all experience. Your hippocampus helps with the formation of new memories. Memories are not stored at the hippocampus, but this is where they are formed, specifically explicit memories. So those are the memories of things that we can recall, that we can declare, right? And so the mnemonic there, if you see a hippo walking across campus, you'll never forget it. So your hippocampus helps you create these new memories. The amygdala, think of that as almost your emotional center of the brain. So these strong emotions of anger and aggression. We can think of the amygdala is helping us regulate these strong emotions. If you stimulate someone's amygdala, they become very angry and very aggressive. If you remove someone's amygdala, they don't experience fear. So you can think Amy Godala is really upset. She's upset because she has a silly last name. And then the basal ganglia. Basal ganglia helps us with fine motor control, so those little tiny movements. Cerebellum are big movements, like riding a bicycle, swinging a baseball bat. The basal ganglia are the small movements, like tying a necktie or playing a violin. If you're chopping up basil, you want to make sure you have fine motor control so you don't cut your finger. Throwing up gang signs, the psychology gang sign. You want to make sure you don't mess up the psychology gang sign, or you might get into a gang war with AP chemistry or something like that. That's the basal ganglia. The brain itself has two hemispheres, as you know, and each hemisphere is divided into 4 different lobes. You can see them listed here. As a really brief overview of the lobes, think the parietal, occipital, and temporal all deal with our senses. Parietal, which is on top, is primarily your sense of touch. Think that parent that bops you on top of the head, right? That's your parietal lobe. It allows you to sense that touch. Occipital, it's the smallest of the lobes. It's in the back of your head. Occipital lobes help you see. You can have the 2 C's, and occipital helps you see. Temporal lobe are located on the sides of your brain where your temples are, and they help you hear. And then everything else you can think of is really housed in the frontal lobes. Now, it's not literally everything else, but for the sake of this class, that's really going to help you out. Frontal lobes help with so many different things, like critical thinking, judgment, planning ahead. That's going to be in our frontal lobes. If you're not sure and you had to guess, I always say guess your frontal lobes. And then covering your 2 hemispheres is your cerebral cortex. Your cerebral cortex translates to bark, right? Like the surface of a tree. And so if we look at your cerebral cortex, we can divide it into some different areas. We have your somatosensory cortex. And the somatosensory cortex is what is active when we feel a sense of touch. And depending on how sensitive these areas are, they have more cortical space. And so a big chunk of your somatosensory cortex, for example, is dedicated to your fingertips, to your lips, because we have a lot of neurons there to interpret touch. And it's very similar to our motor cortex. Our motor cortex is the band that's directly in front of the sensory cortex. And your motor cortex is sending information out from the brain of movement. And the more specific movement that we need, the more cortical space we need to have. So you've got a lot of your motor cortex dedicated to things like your hands and your fingers. You have a lot of your motor cortex dedicated to your face, because we have really specific movements with our hands and our face. Whereas, your chest, your legs, your knees, there's not as much cortical space or area in the motor cortex dedicated to that, because you don't need very specific movements. Now, if we remove the motor cortex, if we subtract out the sensory cortex, everything else that is left over is what we call the association areas. And so in this image here, it's like all of this kind of peach color here that we would call the association areas. And that's where we house things like memory. That's where we house things like language and our ability to communicate. A couple specific areas of language are what we call Wernicke's area and Broca's area. Remember, Wernicke's area is your ability to understand and to comprehend language. Like right now, when you're listening to this lecture, Wernicke's area is hearing these sounds that I'm creating and able to decode that into meaning. And then Broca's area is what allows you to actually create language verbally and to talk to someone. It helps coordinate the muscles in your face and jaw and vocal cords to create what we call productive language. Real quick here with the lateralization of hemispheres, you likely recall that the left side of your brain helps control the right side of your body and vice versa. Other than that, there's not a ton of differences between your left hemisphere and your right hemisphere. The whole myth of some people are left brain or right brain has really been debunked by scientists. However, two things that are worth noting. Know that language resides almost exclusively in the left hemisphere. You can just remember left is language, left is language. Vernix area, Broca's area, those are both housed in the left hemisphere. Your right hemisphere, on the other hand, is really more in charge of like spatial tasks and things. And so it's not that someone like Picasso was just constantly living in their right brain. That's really not it. But when there are spatial tasks like solving a maze or drawing a piece of architecture, we do tend to see more of that take place along the right side of the brain. And then this is our last slide, and it's simply how do we learn about the brain? Well, for a long time, the way that we learned about the brain is by accidents happening. So the story of Phineas Gage having a 3-foot iron rod shot through his brain, and then finding out, okay, this is how he's now reacting. That tells us a lot about what is housed at that part of the brain. Luckily, we don't have to, wait for these horrific, traumatic brain injuries to take place to learn about the brain anymore. Instead, we often use brain imaging. And so I have some different types of brain scans there. Remember, the thing that CAT scans and MRI scans have in common is that they show us a picture of the brain. CAT scans use X-rays, MRIs use magnets. CAT scans are a little bit more affordable. MRIs give us some more detail. PET scans and EEGs both show us activity. So as CAT scans and MRIs show structure, PET scans and EEGs show activity. PET scans use this radioactive glucose, and it shows us specifically where blood is flowing to the brain, while EEGs show us the specific brain waves and how quickly your brain is processing. And then finally, fMRI, that stands for a functional MRI. And fMRI kind of does both. It shows us the structure of the brain, but also the activity of the brain through live imaging. And so it's kind of, the overarching umbrella of all brain scans. So that is perhaps the fastest I've ever talked about the brain in AP Psych, but I hope that it helps refresh your memory about some of these big terms, and good luck.